Hello, and welcome to Variation Inference, Part 5. So we have done quite a bit. I am Chieh from Northeastern University. And so far we've gone through the first portion of the variational inference derivation. And this is where we left off here, like this point here. Now, if you probably want to go back and review the video if you don't remember how we get to this point. But over here, this is the lower bound. And we have been essentially just simplifying the lower bound to come up with some eventual decision about it. So the first thing I'm going to do is I'm going to split this k to equal to k equals k1 plus k2, okay, which becomes here. And we're really going to concentrate on this section here. So let's look at this part for now. And I want to show that that this here, oh, this doesn't belong. So is equal to the log of some function. So we know that this is some function right here, expectation, that's some function, and then this is some constant. And obviously, if you have some function plus some constant, is also some function. But the thing that I want to show is that this is not just any function. This is actually a probability distribution. And this right here is a probability distribution, which has the characteristic of summing up to 1, and that this is always possible. Well, first thing we do is get rid of the log. Therefore, we essentially put an exponential here, right? Which you can see it right here. Now it's the exponential of the e expectation of log of p of x. This part here, maybe I should use a different color. This part here is just a constant. We'll call it c. Over here is some function. And this function, if you were to take the integral over the entire thing, will have some value. As long as c is equal to 1 over the same value, this is a probability distribution. So c is just some constant that we could pick. Remember over here, we split k between k1 and k2. So we just have to pick k1 so that this whole thing becomes a probability distribution, and the rest we just put it in k2. Now, if we do that, we can then make the statement that this thing here is equal to the log of some probability distribution. Okay. Now, if we can make this statement, right, we can then plug this part in right here. So remember, here's k1 and k2. K1 got absorbed into this function. And this is part 2 over here. Okay, well, now that we have simplified this portion, I'm going to move this back out to part 3. See, over here, I moved it back out. And so this part 1, is now much simpler because we had this constant to use right here. Now, the next thing to realize is that, well, if we sum up QZ, every possible combination of QZ, it becomes 1. Like this whole thing becomes 1. And therefore, this is just some constant K2. Oops. Okay. Now, if we do that, we'll just call it K2. And over here, I can now combine part 1 and part 2. Because notice this is QZ1, summation of QZ1. We can combine the summation of QZ1 here, like that, both goes here. And we'll combine the log. See, subtraction in log is division. So you see, now it turns into a division where this, like I said, goes here, and this goes here. And now we have simplified the lower bound even further, such that it's just like this here. And we want to maximize this. We want to maximize this. Of course, when we're doing maximization or minimization, we don't care about the constant. So this could be crossed out. So what we have left over is basically just this portion, right? Just this portion. And that's what we're trying to maximize. This right here is actually a lot easier to maximize because, well, first of all, we're only looking at QZ1 instead of QZ 1, 2, and 3. Now, the next thing you have to realize is that this is also the negative KL divergence of, okay, well, if you find the negative, if you find the KL divergence, you'll get this formula. Notice how this formula, oops, what did I just do? Oh, here we go. Yeah, so sorry. This is the KL divergence. Notice how the KL divergence of QZ and FXZ is the negative of the lower bound. Like, take a second. See, over here is the same. Over here is the same. And over here is the same. So they're the same. The only difference is that this is negative. Okay. Now, if you want to find the maximum of something is the same as finding the minimum of the negative of that something. Therefore, finding the minimum of the KL divergence is the same as finding the maximum of the lower bound. I'll say that again. Finding the minimum of the KL divergence of these two functions is the same as finding the maximum. Okay? So when we want to minimize the KL divergence, and that it's the same as maximizing the negative KL divergence, we can now say that our new goal is to minimize the KL divergence of this. Of course, we already know how you minimize the KL divergence. If the numerator is and the denominator, if they're equal to each other, that's the lowest possible KL divergence because it says that they are the same. Therefore, we pick QZ that minimizes the KL divergence, and the best QZ is equal to this, Fx of z. Okay, well, remember what we said this was. What was this? This was the function that described log f of x and z. It was the expectation of this here, plus some constant. I think it was k2 or something. Now, we'll get rid of the log by taking the exponential on both sides. And this e of k, we'll just call it some constant. And now here's the expectation of log of x and z. And this right here, if you remember, this expectation was equal to this here. See, some PDF and some function. Some function, some PDF. So what I'm saying is, therefore, f of xz, which is equal to qz1, is equal to this function here. We have the c, expectation, the summation of this whole thing. Now, if you had done the same thing, but instead of pulling out qz1, we could pull out QZ2. It would have been in this form. And if you have pull out QZ3, it would have been in this form. And the pattern that I want you to see is that when we're talking about QZ1, notice that QZ1 is missing here. Now, if we're dealing with QZ2, notice that QZ2 is missing. This is 1 and 3. Now, if we're doing QZ3, notice that QZ3 is missing. So basically, this portion is the product of all of the functions. All of the functions. Except the one we're looking at. One we are looking at. Okay, so now we have a formulation that tells us each QZ1, QZ2, QZ3. If we can find them, then we have QZ. Remember, QZ is equal to QZ1 times QZ2 times QZ3. So now we have a formula to find all three of them. There's a slight problem, and the problem was our assumption that, well, we can't find QZ1 because we don't know QZ2 and 3. And we can't find QZ2 because we don't know QZ1 and 3. So it's like a chicken and an egg problem. You need QZ2 and 3 to find QZ1, but you need QZ1 to find QZ2 and 3. So that's a very obvious problem we have. And on top of that, we don't know what this constant is. So there's actually a trick. And the best way, I think, to show you, we don't know them. The best way to show you is, I think, through an example, how this could be done. So let's say we have this. This is the joint, right? We have X, Y, Z. Instead of Z1, Z2, Z3, I'll just call them X, Y, Z. And this is the function for X, Y, Z. So remember, we want to estimate P of X, Y, Z here with Q of X, Y, Z. Now, the first assumption we make is that they're independent, so we can separate them out, okay? So according to this equation above, we know that log Q of X, which is the first one, is equal to the expectation of Y and Z. Remember, it's everything except X. So it was Y and Z of log of the joint plus some constant, okay? Okay, well, if you're finding the expectation of Y and Z, that's the same as finding the expectation of Z first, and then finding the expectation Y. And let's just plug this part in. Now, here, where was it? Yeah, over here. So this is the formula, and I'm just going to plug it in here, which becomes this here, okay? Well, we don't actually have to solve the integral. Notice that we can just find the expectation of this whole thing. If you find it, well, this is a constant, so that comes out. This is a constant because we're looking at expectation of Z, so that doesn't matter. This is also a constant. The only thing you really care about is expectation of Z here. So this whole thing just becomes this. And now we can do it again and find the expectation of Y, okay? Well, this again, this whole thing, right? I'll use the red. This whole thing here is a constant with respect to Y. Over here is also constant with respect to Y. It's over here that it becomes expectation of Y here. And then this part is a constant as well, plus the constant. Okay. And now we can get rid of the log by doing the exponential here. If we do that, you will notice we can pull out this. I mean, this is a function of X, so we only care about X. And everything else is actually just a constant. Well, you might know from the probability class, a stochastic class, that this here is an exponential distribution. So if this is an exponential distribution, this C must equal to lambda 1. Because that's the only way. This is the only way that the integral, like if you have an integral from 0 to infinity e to the minus lambda x d x equal to 1. Because this is the probability density function, c must equal to lambda. And therefore, we actually didn't need to know anything. It just automatically tells us the result that q of x is equal to lambda 1 e to the minus lambda 1 x. Like that was pretty convenient. We didn't have to go and solve anything. So what the trick that I'm trying to explain is that, well, we just go and find the expectation, and then we try to make it look like some other distribution and just make a guess on the rest of the parameters. And this will work a good deal of the time, especially if the joint distribution was really independent of each other. But that's not always the case. There will be times that like that might not work, and I'll show you how to deal with that. Okay, of course, if you use the same logic, you'll end up getting these three. You'll end up getting these three probability distribution, like q of x, q of y, q of z, and they actually are exact. Exact results. Like, even though it's supposed to be approximation, but this one happens to give you perfect approximation. Now, like I said, that was a simple example, but what if we can't get rid of them, right? What if somehow, like in this case, we were lucky that we just found this and that this whole thing turns into some kind of like a constant. But what if we couldn't do that? Like, so what we do is initially, you just pick this value. Expectation y, you don't know what it is. Just pick one. Pick something. And then do the same for this one as well. So once you pick something, you will end up getting like q of x, right? Then you use q of x to go and solve q of y. And if there's something you don't know, you just pick something again. And you use q of x and q of y to pick q of z. And now you have three of them. You go back using what you calculated and calculate q of x again. And this time, the result you get will be closer. And then you use whatever you calculate here to calculate q of y. And then you use that to calculate q of z. And you do this you basically do this circle over and over again until eventually, like, the numbers of like expectation x, expectation z, expectation of x, eventually these numbers would like start converging towards the correct answer. And once it has converged, it will give you, that's when you stop, because the number is not changing anymore. So that's how you would go about doing variational inference. So I hope this example right here I show was informative. Like this example here was informative of how you can go about doing variational inference. Like I said, the key is really like finding the expectation outright and then making it look like some distribution. If you can do that, it will just make the whole process a lot easier, because it allows you to guess the rest of the parameters without actually calculating them. So anyways, I think that is it for video 5. In the next video, if I decide to record one, it might be a more complicated example. So thank you for watching. Bye-bye.